My plan for this session is that I will introduce the use of SAP 2000 for a few seismic analysis procedures which we currently apply on our building structures mostly. Instead of like having a hands-on training session or like step by step uh, kind of a tutorial, what I will do is that I will make an overall demonstration mostly focus on the analysis capabilities of SAP 2000 and how you can use it for several seismic analysis procedures. So I will start with a basic overview of the program itself, several modeling options which this program offers, and then we'll shift to the application of different seismic analysis procedures. For example, as Dr. Mohammed Reza mentioned, the equivalent lateral force procedure as prescribed in ASC 7. So let's start now, and before I directly go to the software demonstration, I would like to quickly give you an overview of this program. So SAP 2000, as you might already know, that it is a general purpose computer program to perform modeling analysis and design of structures. So it offers several modeling capabilities. It has almost uh, all kinds of structures which you can model here. Different complex geometries you can see here. You can model and then analyze using finite element analysis. This program is available here on this link. It is from Computers and Structures, and you can, for the purpose of learning, you can have a trial version first for 30 days, and then you can also go for a commercial or academic license. So before I actually directly go to the program, let's quickly look at uh, the underlying principle on which this program works. We all know that it is a finite element package, so mostly it implements the FEM analysis formulation for the computer models which you create in that program. So a quick review of the basic idea or basic concept about how we can think about the working of this program. So we know that the concept of stiffness actually comes uh, from well-known Hooke's law, which simply states that the force, the displacement produced in any object which have a stiffness k is proportional to the force applied in a linear range. So we already know this simple equation for a simple uniaxial spring already. In the context of real buildings, when we apply the same concept, we represent the stiffness of our structure using the global K matrix or stiffness matrix, and then the force applied is mathematically formulated in the force vector, and then the displacements are computed as the displacement vector. So the order of these matrix K matrix is same as the number of degree of freedom. Uh, in context of seismic analysis, or especially the dynamic analysis of building structures, instead of a force, we have a ground acceleration. We shake our structure's base with that acceleration, and in that case, the governing equation of motion is not simply F is equal to KU, but we have this complete equation of motion for ground motion for our structure. So it has an inertial term as well as a damping term added to that equation. So I think in structural dynamics course, you are well familiar with this mathematical formulation for dynamic analysis, and there are different procedures to solve this equation. So when we say that we are performing static analysis using ETABS or SAP 2000, essentially we are referring to this one, that the program is essentially determining the global stiffness matrix of your structure while you are modeling, and then when you are applying load, it is determining the force vector, and when you are running the static analysis, it is solving this equation of motion F is equal to KU. If you are running the dynamic analysis using a real earthquake ground motion, uh, which is represented here as the UG dot dot function of time. In that case, the program will be essentially solving this long governing equation of motion, and obviously the results will not be constant numbers, but they will also be the function of time now. So the displacement vectors and all other associated responses, they will also be the functions of time. So when you are actually drawing your structure in SAP 2000 canvas environment or ETABS or any other finite element program, you can literally think of it as you are providing the K matrix to your structure. When you are assigning masses, you can think of it as providing the mass matrix of your structure to the program. And then when you are assigning, for example, the damping properties, you are actually telling the program how to construct or the damping matrix or C matrix actually. So uh, just before going to the program itself, let us quickly decompose, because this sequence which I will be using to kind of decompose the K matrix or stiffness matrix will also be used in actually learning how to use the program itself. So let's quickly think about how stiffness of a particular structure is made of, or what constituents it is composed of. So in order to give you an idea, although this particular topic might already be discussed in the finite element course or structural analysis courses, but just to have a quick review, you can see here that I show the local stiffness matrix of one two-dimensional frame element which has 6 degrees of freedom, 3 degree of freedom at each end or each node. And if you closely look at this stiffness matrix formulation, you can see that it is made of actually three types of properties. First is the material property, which is the elastic modulus of the material from which this two-dimensional frame element is made of. And second are the cross-sectional properties like cross-sectional area and second moment of area, moment of inertia. These are the properties of the shape of cross-section. And third one is the length, which is the member property. Actually, when you define a member, actually the program actually gets the length of that section. So exactly the similar sequence we will be following when we'll be using ETABS or SAP. That first we start with the definition of material properties. Program will get the Young's modulus for each material for elastic modeling, and then we will be defining the cross sections, cross sectional shape, which will tell the program about the cross sectional properties which it can calculate. And then we will be actually using mouse to draw our structure, which from which the program will get the lengths and all other member properties. So using this one simple example, you can see that the stiffness of the whole structure is actually made of these three levels of properties. You start with material, then cross section, and then member, which actually constitutes the stiffness of the full structure. So this is the same hierarchy that you start with, for example, material, definition of material stiffness by providing the material properties. Then you add the cross-sectional geometry to that, and it results in section stiffness. So the cross-section stiffness is actually a combination of cross-sectional properties as well as material properties. And then the member stiffness, which actually is the next level. So after defining cross sections, you actually define the members or draw the members or model the members. And then finally the last level is the structure stiffness, the global stiffness of the structure, which is a function of structural geometry, which is actually derived from the member stiffnesses, which is derived from the cross section stiffness, and ultimately the material stiffness. One thing to note here is that the all these stiffness relationships, they may be linear or non-linear. So for the purpose of today's demonstration, I will be only focusing on linear modeling and linear analysis. So we will be assuming that our material, section, member, and full structure, they all are they are all linear, which means their displacements or deformations are essentially linearly proportional to the applied actions. But obviously, nonlinear modeling is a detailed topic in which we actually uh, define nonlinear actions or versus nonlinear deformations at appropriate stages of this hierarchy. So there is a nonlinear modeling approach which focus on material nonlinearity, or there is a separate approach for cross-section or member nonlinearity. That is a whole different topic, and but today's demonstration I will be focusing only on linear modeling and linear analysis. So our focus for static analysis will be F is equal to Ku, and for dynamic analysis the complete dynamic equation of motion which you have seen in the start. So if we look at a typical finite element uh, program, we can what activities we can define in modeling, analysis and design of structures in them. We can divide them into three parts. First is our own tasks, which for which the finite element program will not help, that we have to do ourselves. Second type of activities could be which we provide to the finite element software, and the program use um, those properties as an input. And then finally the third type is the program are the activities which the program can do for us. So for example, the structural idealization or discretization are the first two activities which obviously the program will not help us. We have to first idealize the structure. I call it like step -1, because it is even uh, before the start of modeling process. So you have to idealize your structure, and then after that you have to think about how will you discretize that structure into a finite element program. So the selection of elements and the discretization scheme is actually this part. So again, the program will not help you in deciding the best discretization scheme for your structure. So these two steps obviously you have to do yourself. And then the green part starts actually, which is the properties which we provide to the program while modeling. So again, I divide them into four parts: material, cross section, member, and then full structure. So while you are performing all those activities or definitions, what you are essentially doing is you are providing the global K matrix of your structure to the program, and then you apply load. After completing the model, you apply load, and which essentially means that you are providing either F vector or the F of t vector, depending upon whether your loads are static or dynamic. Then you can also apply the support conditions. So all of these green boxes are the inputs which you will be providing to the program. And then finally, the program can run the analysis for you. It will solve F is equal to Ku, uh, the detailed matrix equation of motion for your full structure, if it is a static analysis, or this complete equation of motion, the inertial force plus damping plus static elastic restoring is equal to the dynamic force. This complete equation of motion if the analysis is dynamic. It will also do the post-processing and the determination of local forces and all the associated responses. The primary output from running these equations is the displacement vectors, which can be converted into local forces and all other responses. And then after that, some programs also offer the structural design process. They can automate different design codes to produce the design outputs also, but obviously they should always be uh, you know have a skeptical view, because uh, the actual structural design process requires a lot of decision making which the program can do for you, and if you are not very skeptical about results, obviously you can have some errors or uncertainty in your design output also. So for the analysis part, 7 or 8, you can completely rely on the program, because the mathematical theory is a unified theory, and uh, and obviously it is an accurate mathematical formulation which the program implements. It doesn't depend on the applied on a particular building code or any particular provisions or compliance mechanism. But structural design obviously requires all of those things. So there is a lot of decision making involved at this step 9. So you should always use the program with great care if you intend to use it for structural design also. And finally, detailing obviously is an important part that again most of the finite element programs will not do for you, and you have to do it yourself. Obviously for CSI there is a CSI detailer also which can help you in detailing and provide the construction drawings and all other structural drawings. So this is an overview of how we will normally work in any finite element program, including SAP 2000, ETABS, and other programs. So let's quickly have a breakdown of those 4 steps, because for this demonstration, today's demonstration, we will be mostly focusing on the from 1 to 6, the inputs which we have to provide to SAP 2000, and also we will be focusing on linear modeling and linear analysis. So let's have a quick breakdown of first step, which is the material stiffness. Obviously, we'll be focusing on linear modeling, so we'll be defining elastic materials. So the properties which we have to provide are, for example, the Young's modulus, the Poisson's ratio, the shear modulus, and the coefficient of thermal expansion. These are the elastic material properties which the program may use in the analysis, static analysis, for example. But we'll not be focusing on inelastic materials for today's demonstration. But again, the idea is that the material stiffness can be defined using elastic materials or inelastic materials. In case of, for example, inelastic materials, we have to provide the complete stress strain behavior and the associated cyclic behavior in order to completely define it. But that is a whole different topic, and we will not discuss that today. For section geometry or cross-sectional stiffness, the second step, we will be simply defining the shape of cross-section from which the programs will determine the basic cross-sectional properties like area, moment of inertia, or other shear areas, for example, for the purpose of use in the analysis, linear analysis. Then member geometry, obviously we'll be simply draw the members and essentially telling the program what are their lengths, what are their orientations, and all that. So we'll complete the full structural geometry at the end, which will help the program in formulating the global K matrix of the structure. So finally we'll be having the structure stiffness at the end, which the program will be using to solve the governing equation of motion and produce all the responses against our applied loading. So this is the overview of the menus which are available in SAP 2000. So mostly you will be using them in the same order, roughly the same order. So you start with, for example, defining materials in this particular menu, and then in the draw menu you will be having the options to actually create the geometry of the structure, and then you can select a particular element to modify it or assign property. So in order to assign a particular property to a selected element, you will use this assign menu. And obviously analyze menu is for analysis. Once you complete the model, apply the loading, then you can also then you can go for this analyze menu. Applied loading will be actually assigned in this particular assign menu. You will be selecting a particular element and then go to assign and then apply the loading. After the analysis, you can display all the results in this display menu, and once you are completing the analysis, you can go for this design menu at the end if you want the program to also produce the design output for you. And then the last is the options and tools and help which you can explore. So some of the options in these menus are also shown on top and towards the left of this screen uh, as toolbars, which you can You can also rearrange according to your convenience, but mostly the options are organized under these headings. So I think this is the typical workflow which I'll be discussing, but I think let me first give you a quick overview of the workflow and then go to the program, and then I'll come back to this workflow again to show you again that this is a typical flow which we do. So first we start a new model in, and this by the way is applicable to both ETABS and SAP. So first we start a new model in which we have to select units here, and also a template. If we want to select a template for a structure, we can use that. And then we go to the definition of materials. As you have seen that this should be the first step in defining the stiffness of the structure. And then the next step is the definition of cross sections. And obviously when we define cross sections, we have to associate a particular cross section with materials. So that's why I just enclosed that material in the definition of cross sections box. After defining the cross sections, we define the elements. Actually, we model or draw those elements using mouse, and this will complete our model. Then we will go to the next step, which is defining load patterns, and this will be the first step towards formulating the F vector or F of t vector, the applied forces vector. After definition of load patterns, we will be assigning different loads to different elements, and while we are assigning them or defining them, we have to include those loads into a particular load pattern. So then those load patterns actually should be called in the load cases. The analysis will be performed in load cases, will be performed for load cases actually, and those load cases can also be called combined to get load combinations, which we can use for design purpose. But actually the analysis is performed for cases, and for linear analysis the results of individual linear load cases are combined according to the defined load combinations, and those combined results can be used, the program can use them for the purpose of structural design. So once you complete the definition of loads, you go to, for example, the definition of support conditions or joint restraints. And for the purpose of dynamic analysis, you should also define a mass source, essentially telling the program from where the mass matrix of structure should be sourced or formulated. Another step here is that while defining the load cases, if you are actually actually uh, performing the dynamic analysis, you have to define the damping also while defining load cases. So then you will run the analysis finally and then display all the results in the display menu. So I'll come back to that workflow again once I have a demonstration about the program. Uh, One last thing before I go to the actual demonstration is the learning resources which you can explore after this session. This is the SAP 2000 documentation which you can open from within the program, and then you can click any document here and it will be opened as a PDF file. It is automatically stored in the same file directory in which the program is installed. So for example, here I highlighted the lateral load manual, or for example the analysis reference manual. These two documents are very helpful in getting the understanding of how the program works and what are the analysis capabilities of this program. The analysis reference manual also gives you an overview of the different mathematical formulations which are working behind a particular analysis procedure as implemented in either SAP 2000 or ETABS. Similarly, the computers and structures also have a very detailed YouTube channel. You can find a separate playlist for each of the programs which are developed by CSI. So you can check the SAP 2000 playlist, and that is very useful in uh, getting an understanding of the use of this program. So you can check that after this session also. And as mentioned by Dr. Mohammed Raza, I also have a YouTube channel which have a several playlists in which I made demonstrations of either ETABS or SAP 2000, Perform 3D also, and some other programs related to the seismic analysis procedures. So if you look at the overview of all the available seismic analysis procedures, they can be either classified into static or dynamic analysis. And again, the static analysis, depending upon whether you are using a linear computer model or a nonlinear computer model, they can be divided into two parts. One is the linear seismic analysis, and the second is the nonlinear. Obviously, our focus in this particular demonstration is the first column, which is the linear seismic analysis procedures. And there are actually three seismic analysis procedures. You are currently getting familiar with the equivalent lateral force procedure and the response spectrum analysis procedure. But you also have the linear time history analysis method, in which we are using the actual ground motion shaking to shake our structure and perform the dynamic analysis. So this number 3 or number 4 here is the rigorous dynamic analysis procedures. They are the linear time history analysis, but again they have two different mathematical formulations. The number 3, which is the modal response history analysis, uses the idea of mode shapes to determine the dynamic response of each mode of the structure separately and then superimpose them to get the combined dynamic response. The number 4 actually is based on the direct integration, which directly computes the dynamic response in a step-by-step direct integration scheme. So actually 3 and 4 both are the rigorous dynamic analysis procedures. But first two are essentially static. Why I use the response spectrum analysis somewhere in between static and dynamic is the reason that the actual application of force vectors in the response spectrum analysis is static, but those force vectors are determined based on the mode shapes of the structure. So some dynamic characteristics of the building or structure are involved in determination of those force vectors, and therefore it can be sometimes called as a dynamic analysis procedure in different building codes also. So this first column will be our topic for today's demonstration, and we'll be not discussing the nonlinear modeling and nonlinear analysis methods. So I have you can say the a separate playlist, uh, lecture playlist or demonstration playlist for each of these methods, linear as well as nonlinear. So maybe after this session in later part of this course, maybe you can check that. So I have a separate playlist for ELF procedure, response spectrum, then linear time history, then nonlinear modeling, and then nonlinear static procedures, which are also called pushover analysis procedures. So you can check all those lecture series or demonstrations at later stage. For today's demonstration, I'll be using this very simple reinforced concrete structure. It is a 10-story reinforced concrete building, and it is a combination of shear walls and moment resisting frame. It has a constant story height of 3 meters. I'll be using Newton millimeter units for this particular structure, but you can use any units you are comfortable in. And for simplicity, I'll be using all the beams same cross section size, all columns as same cross section size. Similarly, slab thickness and shear wall thicknesses will be all constant. Obviously, this is not a real building. I'll just use it for the purpose of demonstration. A real building will have many different types of beam cross sections, column cross section, slab and shear wall thicknesses. For material properties, I'll be using these concrete and steel material properties, uh, and they will be assumed constant for all elements. But obviously, in real structure, you will be having uh, different types of materials for both concrete and steel and some other materials also. So this simple model I'll be using to demonstrate some of the seismic analysis procedures, or you can more accurately say as the analysis capabilities of SAP 2000 for these uh, this particular structure. So this is a plan view, a very regular plan, that it has a core wall in the middle and a few planar walls at the outer periphery of this structure, and it has a constant span length in both x and y, global x and y directions. So now I'll be shifting to the program demonstration for this simple structure.